This video starts the second half of Chapter 7 for Chem 103, starting with Section 4. And I've asked you to watch a different video before this one, and that's a video from Veritasium that showed in a really nice way how light can be considered both a particle and a wave. And we've learned a fair amount about light at this point. And we're now going to move on to considering how that interaction between light and matter tells us more about electrons. So electrons, based on the experiments of scientists in the late 1800s, early 1900s, we know something about electrons. We know they have mass and charge. We have actual values. They're quite small, but we have actual measurements of the mass and charge of an electron. So just the fact that we have those pieces of information makes us think that an electron would just be considered a particle, right? But at some point, scientists started considering the possibility that electrons could act as a wave as well. And we know that particles, streams of real particles with real mass, don't form interference patterns like waves do. So the question was asked, well, what if we have a stream of electrons? They're so small. Yes, they have mass, but I wonder if they would form interference patterns. This is a really innovative question to ask. No one really thought that electrons would create diffraction, create interference, but it was found that they did. And these two pictures here, the first is an image of X-rays passing through a crystal. And these patterns that you see are similar to what the Veritasium video showed with the light. Waves of X-rays interfere with each other and create these diffraction patterns. And a similar thing is seen when we pass electrons, streams of electrons through that same type of crystal. And we see electrons interfering with each other and creating this very similar diffraction pattern. So the physicist who was mostly involved in this research was named Louis de Broglie, and he was the one that kind of first posited that electrons might have both wave and particle properties, and he came up with an equation that would give us the wavelength of a particle. There's a really nice kind of derivation of this equation in your textbook. I would take a quick look at that. But we'll focus on actually the applications of this equation from here on out. And the equation gives us the wavelength of the particle based on three other variables. H is Planck's constant, so that's that value that we've seen before, 6.626 times 10 to the minus 34th joules times seconds. M is mass, and U is speed. We've used lowercase v for velocity or speed in the past. For whatever reason, your book kind of jumps around a little bit. But the lowercase u is velocity or speed. So let's take a look at what this equation shows us. It's kind of weird to calculate the wavelength of a particle, but we'll see why it's important for electrons. And we'll do this by comparing an electron to a ping pong ball. So basically what we need to apply this formula is just a mass and a velocity. We have Planck's constant. So let's assume that an electron travels at 1 times 10 to the 5th, or 100,000 meters per second. We can look up the electron's mass, and let's assume that the ping pong ball has a mass of 11 grams and it's traveling at about 2.5 meters per second. Seems reasonable. So if we plug these values into the de Broglie equation, we find that the wavelength of an electron is 7.27 times 10 to the minus 9th. And meters. If we plug in the values for the ping pong ball, we get a very different value. We get 2.4 times 10 to the minus 32nd, which is incredibly small. And here's the thing. The reason why we will want to consider an electron as a wave is because that wavelength is actually significant. That length, 10 to the minus 9 meters, is very close to the size of the atom. And so therefore the electron's wavelength has implications. With the ping pong ball, the wavelength is so inconsequentially small that it's not going to affect anything about the ping pong's physics, the ping pong ball's physics, or anything like that. It's so much smaller than the size of the ping pong ball. One note here too, the Planck's constant, you can see the units are a little different from what we've used before. This is just an alternate way to represent the units of joules times seconds. So to summarize, we can talk about photons and we can talk about electrons as both having particle and wave natures to them. And there's different equations that, that kind of allow us to quantify some things like wavelength and energy. So for the photons, for light or electromagnetic radiation, you've seen all of these equations before. And now for electrons, we have kind of a different set, so let's look at those more carefully. This first one for the energy of the electron is one we've actually seen before. It's 1/2 mass times velocity squared. And so that's just telling us that we can calculate the kinetic energy of a particle if we know its mass and velocity. The second equation here is the de Broglie equation for the wavelength. And then the one for speed is just a rearrangement of the equation for energy, but solving for the speed or velocity. So that wraps up our quick video on the de Broglie principle and considering electrons as both particles and waves.